Hello. Today I will talk about the topological Markov change. So, before I start, let's recall some of the concepts. For example, the shift map. This is basically um, if we have an alphabet that could be from a number to 1 to k, we can generate sequence. This is basically a sequence. The sequence could be finite or could be infinity, and also could be in both sides, right? Okay, the shift map basically is this function sigma that will go from this alphabet to another alphabet, and is defined by the switch. For example, the sigma w, if w is this one, it will start now from 2 3 instead of 1. Okay, that have some similarities with the computer science theory of computation, that we also have the set of the elements that we can have the alphabet, and is also called with this uh, addition symbol. And a string, word, or sequence is basically, as I said, a sequence of these elements that could be infinity in most of the case. The two-side sequence is exactly what we have here, but with the exception that whenever we get into 0, we started going in negative. So the numbers, instead of going in the natural numbers, we will have into the integers numbers. Okay, and also we call it that sequence, a point is periodic if we have this, if the values of the digits are repeating, let's say n times or m times. If we have this for any n that belong to the integers, in that case we call it that this point is n periodic. Okay, so let's now start with the topic. Okay, the topological Markov chains, that we also call it subswitch of finite type, are this. This is the definition that we have from the book. By the way, I am using this book. This is the book from the Barreira and Valls, where I am getting all the definitions, and I am also using this book from the computer science. This is theory of computations, where I got some of the similarities that we have from the topological Markov chain with the finite automatas, and you will see in a moment what are these. So from the book we have that given an integer k is greater than 1, we have a point in the matrix A. The matrix A is the transition matrix. We have a point I from the matrix k by k entries. We will have that these values could be 0 or 1, right? So we have a transition or we don't have a transition. For each A and J, we construct the subset. This is the set that we basically are going to utilize to create the matrix, defined by the words that belong to this only happens whenever these entries is equal to 1, right? What I say, let me just explain a little quick here. If I have the matrix, let's say the matrix A, let's say that for this k could be 3, right? For example, could be 3, and will be, let's say, a no, let's call it differently. L center right, so I have L center and right and L center and right. If I say that we will have transition from L to center, we will have a point here, or if we have another transition from right to left, we will have another transition here, right? So in this case, A, because this is 1, 2, 3, 1, 2, 3. If we have A 3, 1 will be 1, it means we have a transition from right to left. Okay? If we don't have values there, basically we will have 0, 0 everywhere, right? I put it this one like this. So this is adjacency matrix in graph theory, but here is a transition matrix, and basically works very similar. And that is what I said here. Whenever these values are 1, then the sequence that happens to have these rules will belong to this set. Okay? So what this means is this is a subset. This set is a subset of the biggest set with all the combinations of sequence that we can have using the alphabet K, right? So the definition is the restriction of this function, the switch, to only the sequence that have that happens to be in the transition matrix and are valid sequence are called, this is called the topological Markov chains with the transition matrix A. Okay, so this subset is generating a language of all the possible combination of sequence that we can have. Only the subset of sequence that have this transition matrix valid for that sequence, that are valid for the transition matrix, then there will be a language in computer science terms, but here it will be the topological Markov chains with the transition matrix of A. So I have an example here how it works. Okay, let's say this matrix, we have the transition from 0, we have here two numbers. We are not calling what numbers are there, but the first one to the same one this is a transition that is not happening. However, the first one with the second one is a transition that is happening. The last one, see, that is a transition with the same one. So this is the only fixed point that we have here. So, and we can interpret this in the same way that we did it previously. If the entry, this entry is 1, then the word will belong to this set. If not, it will not belong to the set. In this case, what we are saying here is that whenever let's say this is 1 and this is 0, 1 and 0, and for this case in particular, we have 1, 0. This is my alphabet. Okay, whenever we have from 1 and we are going to do a transition to 1, it will not happen, right? So the subset of all sequence in this set, which the symbol is 1, is always isolated whenever it occurs, right? This is the case A is a restriction that is defined a language over this set. This is what I said. So if we see the similarities with the computer science and automata theory, we have this. This is the incidence matrix. You know what is this? This is the finite automata that we have here. So for example, to go from the numbers from the element 0, we can go to 0 many times, any times that whenever we want. However, if we go from 1, the only way that we can go is coming back to 0. See? If we go to 1, if I am in 0 and I'm going to 1 next, in the next iteration, if I wanna go from 1, the only road that I have is going to 0. I cannot go to 1 again. I can go to 0, and so on. So, and this, I put it this is the sequence, and this is how we are doing the transitions. And these transitions is very similar to the Turing machine. The Turing machine is this. We have the elements, the k elements. We have also the set of the transition set. We have the transition function. We have the starting point and the stop point. But basically, I wanted to just show that we can also represent this using the Turing machine, and this is how it works. This is an example. Let's say we have the transition matrix 0, 1, 1, 0. How it looks like. This is mostly the same. It's telling the same thing, that it will only work whenever the entry for the matrix A is 1. So we have the matrix A here, and this is the transition matrix. So how it would look like from the computer science points. It will look like this. We have the transition from 0 to 1, and from 1 to 0 only. We don't have self cycles in the state. This means the only segments that we will have here is this. Of course, I have put a point here because we have the sequence from the left, the sequence from the right. This is a two-side topological Markov chain. Okay, and these are the only two words that we can have here. Is this one? Whenever we have 1, 0, 1, 0, 1, 0, or whenever it starts from 0, 1, 0, 1, 0, 1. So in this case, W1, whenever we have the switch from W1, it will go to 2, and whenever we do the switch from W2, it will go to W1. So this means that this is the only orbit period of 2 that this matrix, transition matrix, will have. Okay. Another thing that I wanna show here is, let's say we need to determine when the topological Markov change from this set A and to the set B are topologically conjugate. See, so I will put this. If you want to stop for a second and try to solve by yourself, do it. If not, I will show the answer right now. It is not a formal mathematical answer, but it will show you that from computer science we can do similar things. For example, here we said whenever is the name of the value that we have here in the alphabet, we will have a transition to itself in this one, right? We don't have a transition to itself to the second element. However, in this case, I have a mistake here actually. But still, we have a transition to itself here, or itself in this case, but we don't have transition in between. Okay, this is the part of B. So there is no way that we can have a congruency between these two. In the other case, try to do it by yourself if you want for a second. If not, this is the proposed answer from the point of view of computer science. We will have this state, the finite state automata, that yes, it looks in opposite way, but if I can create a function that will map this state with this state and this state with this state, and will create the same words basically. Okay, so now we are going to see the periodic points. The periodic points, let's say we want to have the period 2, right, for this set. That means we need to find the transitions. We need to find the transition that we go transition from E to J, and then and all this transition come back to I, right? For let's say a vector I and J that belong to this set, okay? Or in the matrix, whenever we have the transition from I to J that will go to J to I in the second place, and then it go to once, then we will have this. We will have that the summatory, right, of this transition will be exactly the same as the summatory of the diagonal of the second power of the matrix A. And this is basically what we call it, the transition to the matrix A to the square. So, but how can we get the diagonal of a matrix? If the matrix is diagonalizable, I don't say, how can I say that in English properly? But if we can get the diagonal of this matrix, we will have this. Wherever the diagonal for this IR is the diagonal entry, okay, we will have this property that will work. This is a proposition. For each of the m entries, and the number of m periodic points of the topological Markov chain is equal to the transition to matrix of the diagonal to the power of A, m, power m to the matrix A. Okay? And this is the proof. Basically, it's just a generalization of what we did before with number 2, as well as we did for number 2. The number of sequence W of this set is m periodic, coincides with the number of vectors that we have here that belong to this alphabet, or the transitions I1 to I2 to IM to I1 again, or the transition in A matrix, which is exactly from 1 to 2 and to 2 to 2, 3, and so on, that all these transitions are still in 1. Therefore, the number of periodic points of this set, the topological Markov chain, is equal to exactly basically the same formula, but for all these transitions that will be for A to M. And we can have an example of this. Okay. I'm missing. Oh, okay. This is an example that I have here. So we have again this matrix. Very simple matrix because this is the example that we want to have. This is the finite state automata. Let's say if we are using the symbols left and right, there are only two symbols. We only will have two periodic sequence here, right? From L to right and L to right and L to right, or right to left, right to left, right to left. It's the only one that we will have here, and we are going to prove it here using the proposition that we showed in the previous part. So first, how can we get the diagonal of this? We obtain the determinant by the eigenvalues, the possible eigenvalue multiplied by the this is the unique matrix. So we have basically this, and we have to multiply one of this and this this by the other one, and subtract that from the eigenvalues, and basically we will have two eigenvalues from here. One is 1 and the other is minus 1. No mistake here. Okay, so if I multiply it only by the first eigenvalue, we will have this matrix. Then we can solve when it's going to be 0, and of course we will have this value here that is open to, we can choose whatever we want, and x will be equal to x2, right? Because if I have x1 minus x2 equal to 0, then this will be like this. Okay, so basically the first eigenvector will be 1 and 1. Okay, I put the transpose here because I wanted to just put it horizontal. The same thing we do for the other eigenvalues. Okay, and this is the result. We will have this other eigenvector. So we have this matrix of the eigenvectors. This is the matrix with the inverse of the eigenvector. This is how we do using some of the basic concepts from linear algebra. Then the transition matrix basically will be this one. We have the diagonal in the middle, and we have to elevate these numbers to the power, and the summatory of these numbers is what we are going to use here, which is this one. This is the formula. So in this case, if I have the period 2, the period 2 say that basically we'll have this minus 1 to the square. It will be 1 and 1, the result will be 2. Okay, if I have this to the period 3, there is no period 3 here, so it will be 0. Okay, from the book we have another example, a little bit more difficult to calculate it, but you can do it in your house if you want. But it's very similar. We have another matrix, is 2 por 2. Remember, this matrix could be any side. Just say 2 by 2 just because it's easy to show here. And this is the diagonal that they have. They have also the eigenvectors. These are the eigenvectors. Then this is the a to the power, and what we need to get it, that the transition in order to get the number of periodic points, periodic sequence, are basically, this will be the formula, the summatory of this diagonal to the power n. Okay, this is just a fun fact. These numbers that we have here from the book also are called the golden ratio, and this is the number, and this is the conjugate, this the other one, are also found in the Fibonacci formula that we have here. And it's not just in Fibonacci, it happens in many places in the nature. Okay, finally, in topological entropy, this is super cool, because now that we have defined this transition matrix, we can say that this is a theorem actually. The log of this spectral radius, where this is the spectral radius is of A, is the maximum eigenvalue, the absolute value of the eigenvalue that we have from the matrix A. See? To prove that, actually the proof is here, is detailed in the book, but I just want to give you an idea of what they do in the proof. This is the actual proof for this is in this page. But what they say is that, okay, we have the fact, this is the metric that they are using for some p, that we have the neighborhood that we have based on this metric, on this distance, will be greater than or equal to the transition matrix of A to the Q. Okay. However, we also know, okay, this is the formula of the topological entropy. Explain this formula will be basically a different video, and I will be happy to do it next time. But for now, let's assume that we already have this formula. Will be greater than if we have the entropy for the transition of the A P plus M to 1 plus 1, okay? Which is equal, because this is periodic, right? It is equal to the same transition to M. So in this case, the transition to M will be the summatory of the eigenvectors that we have. Okay, so the spectral radius will be basically the absolute value of the maximum, this one that we have here, the maximum absolute value of the eigenvectors. Okay, I hope you like it, this presentation. See you next time.